So the question here is, for non-degenerately doped N-type silicon, which one of the following plots represents the temperature T, dependence of free electron concentration N, question mark, and their answer is given in all these four options of A, B, C, D. We have to find out the correct answer out of these. And this is the question they had asked for GATE EC 2024 from the subject of EDC. So if you observe this graph, whatever it has given in all these four options, so here x-axis is taken as a 1 by T, that is inverse of the temperature in degree Kelvin, and here this y-axis is taken here as a log N, and for this one we have to find out the correct answer. So we have to understand this word first, what it has written, non-degenerately doped N-type silicon. So this is saying that it is normally doped N-type silicon, for which how the free electron concentration varying with the temperature, that we have to understand, and accordingly we have to find out the correct graph which is matching with the correct option. So now here if we'll see that energy band diagram for the normally doped N-type of the semiconductor, then it is somewhat like this. So here if you'll see that this region, and this is the valence band, this is the valence band having the energy level of EV, this is the conduction band having this lowest energy level as EC, and their Fermi energy level is somehow at this point, this is EF, and this is a donor energy level which we can denote here as a ED. So this is N type of the semiconductor in which pentavalent impurities are doped so that their donor impurities will be residing at this level ED, at this level ED. So for example at this point it is residing the doped atoms here. So at very low temperature or even at the beginning of the temperature, what will happen? This donor electron will migrate from ED to their conduction band here, so that here it will be generating positive ions, and the same number of electron is accumulating in their conduction band. So due to that reason, the concentration of electron will be somewhat higher in this conduction band, and that is called here as a N type of the semiconductor. So here this fifth electron of that pentavalent atoms is lightly bounded with their nucleus. So to migrate from this ED to this conduction band, it is required very little bit of energy, and that we can achieve at very low temperature itself. So as long as this temperature is increasing, what will happen? This donor energy, these electron from the donor energy level, it will migrate from this ED to this CB. So slowly the concentration of electron will be increasing in this conduction band with the slightly rise of the temperature, and after certain point, after certain temperature, there will be saturation. It means by that time of the temperature, all these fifth electron has already migrated from this donor energy level to this conduction band. So there is no further ionization will takes place by that time. So here if you see that how the plot will happen. So as per the option whatever it has given, that this x-axis is 1 by T axis in terms of per degree Kelvin, K raised to -1. So it means 1 by T is increasing from left to right direction. It means temperature will be increasing from right to left. So what I am trying to say that if temperature is very higher, then this 1 by T ratio will be very lower. So that is the reason this is for the temperature axis, whatever I had taken. So it will be opposite to this 1 by T, and this y-axis is taken here as a free electron concentration in, or even we can scale down by taking their logarithm. So log n, this will not change the orientation of the graph, it will be in the similar way, and their unit is per centimeter cube. So how the graph will comes here? So as the temperature increases, what will happen? Their ionization will takes place, and with the rise of temperature, here, their free electron concentration will increase, and at certain temperature there is complete ionization. In that range there is no further change, in the concentration of this electron. So that is called, like, this is the saturation region over there. But at certain point, let's say at this point of the time, there might have very higher temperature. So as we know that once the temperature increases, the carrier concentration, or what we can say that breaking of the covalent bond, will increase, so that intrinsic whole electron pair phenomena will take place with the more dominance there compared to that doping. So in this reason, this is because of the doping. So this is called extrinsic. This is called because of the extrinsic, these things happens, and at this point what will happen? There will be sudden rise. in the concentration, which is called as a at this point this intrinsic phenomena will dominate compared to this extrinsic. So from here, from the beginning point of this temperature, there will be extrinsic phenomena, but at this point of time, what will happen? This intrinsic will dominate. So the reason behind that, here, due to that higher temperature, the breaking of the covalent bond will be much higher compared to how much is the electron because of the doping. So due to that reason, there will be sudden rise in this carrier concentration of the electron at this point. So by this way, this graph or this plot, we will get it for this n type of the semiconductor with the rise of the temperature or with the decrease of the temperature, whatever it is. So here at this point of time, the behavior of this extrinsic semiconductor will change from extrinsic to intrinsic because of the dominance of the intrinsic phenomena. So if we'll compare this graph, whatever we got it here, with the given option, then it is matching with option A. So option A is the right answer for this question, and by this way, this is the end of the explanation for this question. Thank you. So the question here is, the free electron concentration profile Nx in a doped semiconductor at equilibrium is shown in the figure, where the points A, B and C mark 3 different points full stop. Which of the following statements is or are true? And this is their profile given in this figure, and their corresponding statements is given in their 4 options as a ABCD. So we have to find out which statements are correct here as per the question. So now if you'll see that I had redrawn the same plot here, and if you'll see that at this point, at this B point, which is the center point of this graph, so here the electron concentration is maximum. So I can say that it is having maximum electron concentration. And as we know that as per the diffusion process, the charge carrier, whether it is electron or hole, charge carrier always diffuses from higher concentration to lower concentration. So if you see that from middle of this graph, left side is also their concentration decreases, and right side of this point is also their concentration decreases. it means diffusion will takes place in both the direction. Like the diffusion of the electron will takes place from B to A as well as B to C. So due to that reason here, what will happens, as per that we can write it here, that electron is diffusing from B to C. This is here electron diffusion, and the electron is diffusing B to A as well as B to C, both the direction. So as we know that this electron is carrying the negative charge, so current due to that will be in the opposite direction. So diffusion current will allow to flow here from A to B in this left side region. So here we can say that this is the electron diffusion current which is flowing from A to B, as well as for B to C region, that charge carrier as electron is diffusing from B to C, but the direction of diffusion current in this region will be from C to B. So this is called here JN diffusion. And as we know that drift current is always opposite to this diffusion current, so for A to B region, if diffusion current is flowing A to B, it means their corresponding drift current will flow in this direction. So this is called JN drift. And for B to C also, like in this B to C region also, it will be opposite to this JN diffusion. So in this one also it will be flowing in this direction, and their corresponding electric field will be directed in the same direction as like their drift current. So here this will be having this direction. This is for the electric field in AB region, and here in this BC region, this is the direction of electric field. So they had asked in their option, as per this graph, what is the right statement we have to find out. So if you see that in option A, what it has given the statement, for X between B and C, the electron diffusion current is directed from C to B. So as I had given that if the electron diffuses from B to C, their corresponding diffusion current will be directed opposite direction. So this will be JN diffusion. So that will be directed from C to B. So as per that, option A statement is correct here. Now again we have to check it for B. So for X between B and A, the electron drift current is directed from B to A. Yes. So here this electron is diffusing from B to C. So their diffusion will be directed from A to B, and drift will be opposite to that. So for that one, this will be directed from B to A. So for this option B, for X between B and A, the electron drift. So this is called JN drift. So electron drift is directed from B to A. So that option B statement is also right here. Now if you see that for C, for X between B and C, the electric field is directed from B to C. So here if you see that, as I told, if JN diffusion is directed from C to B, it means JN drift for B to C. So as I told that their corresponding electric field will be also in the direction of JN drift for this B and C. So that this electric field will be directed from B to C in this region. So accordingly, this option C statement is also correct here. And for this option D, for X between B and A, the electric field is directed from A to B. So that will not be the correct answer, because here as I told that this JN drift is directed from B to A, it means their corresponding electric field also should be directed from B to A. So due to that reason, option D statement is not correct. And as we had seen, more than one option statement is correct here. So it means this question belongs to that MSQ, multiple select question, and this is the question taken for from GATE EC 2024 from the subject of EDC. So by this way, we got that this A, B, C are the right option for this question, and by this way, this is the end of the explanation for this question. Thank you. So the question here is, consider a MOS capacitor made with p-type silicon full stop. It has an oxide thickness of 100 nanometer, a fixed positive oxide charge of 10 raised to minus 8 coulomb per centimeter square at the oxide silicon interface, and a metal work function of 4.6 electron volt full stop. Assume that the relative permittivity of the oxide is 4 and the absolute permittivity of free space is 8.85 into 10 raised to minus 14 farad per centimeter full stop. If the flatband voltage is 0 volt, the work function of the p-type silicon in electron volt, round off to 2 decimal places, is fill in the blanks full stop. And this is the question they had asked in GATE EC 2024 from the subject of EDC, and topic is MOS capacitor. So first of all, we'll note down the given data here, then accordingly we'll find out whatever they had asked in the question. So here, this given data for this question is their thickness of the oxide layer TOX, it has given 100 nanometer. Their charge at the interface, it has given Q is equal to 10 raised to minus 8 coulomb per centimeter square. Their work function for the metal, it has given QFM is equal to 4.6 electron volt, and their relative permittivity epsilon R is equal to 4. Their absolute permittivity is given here as 8.85 into 10 raised to minus 14 farad per centimeter, and their flatband voltage VFB, it has given as a 0. So what they had asked? They had asked about that work function of the substrate, which is taken here as a p type of the silicon. So basically we need to find out the work function. So that QFS, that QFS means it is the work function for the semiconductor, whatever we had considered here is a p-type silicon, so that we need to find out here. So from the given data, from this one we can say that the Fermi potential for this metal, it will be how much? So this Q and E is cancelling to each other, so that phi m is equal to 4.6 volt. And as we know that the formula for finding this flat band voltage is VFB is equal to work function difference of this phi ms. So this is called Fermi potential difference between metal and semiconductor, minus Q divided by COX. COX is called the capacitance offered by this oxide layer of the MOS capacitor. So this, let's say, as equation number 1. So first of all, we need to find out the COX because Q is already given here. So we have to find out this COX, as we know that from the formula of this COX, how we can find out? This COX can be obtained as a epsilon OX divided by TOX. So this epsilon OX we can easily find out as a absolute permittivity, so that will be given here epsilon R into epsilon naught. So this can be written here as a 4 into 8.85 into 10 raised to minus 14 divided by their thickness, it has given 100 nanometers. So we can write it here 100 into, for this nano we can write 10 raised to minus 9. So now it will become into meter, but we need to change this into centimeter as per the other unit taken here. So into 100. So now this will change to centimeter. So by calculating this, we will get it here as a 35.41 into 10 raised to minus 9 farad per centimeter square. So this we got it here as a COX. Now we can substitute the value of these all the parameters in this equation number 1. So we will get it here. Their VFV, as per the question, it has mentioned that it is 0. So we can write it here as a 0. This phi ms we can write it here as a phi m, that is the Fermi potential for the metal, minus this phi s for the semiconductor, minus this Q divided by COX. So this phi m, as per the given data we had calculated, this is 4.6 volt, minus this is here phi s, minus this Q is 10 raised to minus 8 divided by COX is 35.41 into 10 raised to minus 9. So this will become here phi s is equal to what? This phi s is equal to 4.6 minus 10 divided by 35.41. So after doing this calculation, we will get it here as a 4.32 volt. So this is called the Fermi potential for the semiconductor, but we need to find out here work function. So here we can get it that work function for p-type silicon is equal to this. Whenever we will multiply this by the Q, then this will be multiplied by E. So that is becoming the work function for this semiconductor, which is taken here as a p-type. So this we can write it here, Q phi s is equal to 4.32 electron volt. So the numerical values for this work function of this p-type of the semiconductor is 4.32, because their unit in terms of electron volt is already mentioned in the question part itself. Here you can see that their unit is already mentioned. So their numerical values for this question, it will become here as a 4.32, and this has taken up to 2 decimal places. So by this way, the final answer for this question is 4.32 electron volt. And by this way, this is the end of the explanation for this question. Thank you. So the question here is, a non-degenerate n-type semiconductor has 5% neutral dopant atoms, full stop. Its Fermi level is located at 0.25 electron volt below the conduction band EC, and the donor energy level ED has a degeneracy of 2, full stop. Assuming the thermal voltage to be 20 millivolt, the difference between EC and ED in terms of electron volt, round off to 2 decimal places, is fill in the blanks, full stop. So this is the question they had asked in GATE EC 2024 from the subject of EDC. So now here if you see that this is the energy band diagram, whatever we had made it for N type of the semiconductor. So here this is the conduction band, and this is their valence band, and their notation already I had shown, as well as their labeling. So this is the energy band diagram for N type of the semiconductor. As per the question, if we'll read this line by line, then you will find out that it has 5% of the neutral dopant atoms. So what do you mean by this? So how much we have the dopant atoms here? Out of that, 5% is not going to be ionized. So 5% of that dopant atoms will be lying at this donor energy level. So here these things you have to take into the consideration. And for this question, whatever it has given the information, as per that I had drawn here this N type of the energy band diagram. And in this one it has given EC and EF difference, it has given as a 0.25 electron volt. If you see that here its Fermi level is located at 0.25 electron volt below the conduction band EV, below the conduction band EC. So from this EC, this EF is lying below by the amount of 0.25 electron volt, and ED is lying in between of this EC and ED. So as per the question, they had asked about that what is the difference between EC and ED in terms of electron volt, what we need to find out. So from this 0.25 electron volt, if we are able to subtract the difference of this ED minus EF, then we will get that this EC minus ED. So here, as we know that for this N type of the semiconductor, their equation is given as ND. Small nd is equal to capital ND divided by 1 plus 1 by G exponential ED minus EF divided by KT, where this ND is total dopant atoms. This small nd is what? Which is not going to be ionized, which is neutral, which is lying at this donor energy level. And this G is degeneracy factor, whatever it has given in the question as a 2. So that is here G, and ED, EF, you know that all those parameters now. So here from this one we have to find out. So this Nd will be what? This Nd is not ionized atoms, or what we can say as a neutral atoms. Ideally entire this dopant atom should be ionized, but in the practical case there might have the chances that few of the atoms may not be ionized, so that will be available in the neutral dopant atoms. So here that count is 5%, and that is denoted by this small nd here. So as per the given information, we can write it here. Given 5% are neutral dopant atoms. Neutral dopant atoms. So this Nd will become how much? This small nd is equal to 5% of this total dopant atom. So this will be written here Nd into 5 by 100. So this will become here 0.05 Nd. Let's say this as equation number 1. In this equation number 1, we will put it here, this Nd value, then G value, and by solving this we can easily find out this Ed minus Ef, because this Kt value it has given as a 20 millivolt here. So now in that way we can find out here. So now it will become here, this Nd is small nd is 0.05 Nd is equal to this Nd divided by 1 plus 1 by 2, because this degeneracy factor it has given as a 2, into exponential Ed minus Ef divided by Kt. So here this Nd cancel, and we can solve this. We can take that logarithm, and then we will find out this Ed minus Ef value will be, this Ed minus Ef value is 0.07275 electron volt. So now here, as we need to find out this Ec minus Ed, see here, we need to find out this Ec minus Ed. So it means we have to do this like whatever we have it, Ec minus Ef minus Ed minus Ef will give it here Ec minus Ef. this EC minus ED we can easily find out. So ED minus EF is calculated already here, and this EC minus EF is given as a 0.25. So 0.25 minus 0.07275, and this will be in terms of electron volt. So we will get it here, this as a 0.17725 electron volt. So we can approximate this up to 2 digit after the decimal point. So we will get it here as a 0.18 electron volt. So here we got that this EC minus ED is equal to 0.18 electron volt. This EC minus ED, whatever we have to find out, this EC minus ED we got it here as a 0.18 electron volt. So the answer for this question, it will become here as a 0.18 electron volt. So their unit is already mentioned here. So the numerical values will be 0.18. This is the question based on numerical answer type. So the final answer for this question is 0.18. And by this way, this is the end of the explanation for this question. Thank you. So the question here is, an NMOS transistor operating in the linear region has IDS of 5 microampere at VDS of 0.1 volt full stop. Keeping VGS constant, the VDS is increased to 1.5 volt full stop. Given that mu n COX W by L is equal to 50 microampere per volt square, the transconductance at the new operating point in microampere per volt rounded off to 2 decimal places is fill in the blanks full stop. And this is the question they had asked in GATE EC 2024 from the subject of ADC, and topic is MOSFET. So here in this question what they are trying to ask, that as per the given data, first of all this NMOS transistor is operating into the linear region at VDS is equal to 0.1 volt. By that time in that linear region their IDS is 5 microampere. Then later it is saying that by keeping VGS constant, we increase this VDS from 0.1 to 1.5 volt. Then by that time what will be the transconductance at this new operating point, we need to find out here. So now we are going to solve it. So here as per the given data, in linear region, this drain to source current is given 5 microampere at VDS of 0.1 volt. As we know that this IDS in linear region, the formula is IDS is equal to mu n COX W by L into VGS minus VTH into VDS minus VDS square by 2. These are all the parameters well known to all of you. So here as per the given data, this IDS is given 5 microampere. So we can write it here 5 into 10 raised to minus 6, and mu n COX W by L, this value it has given 50 microampere per volt square. So we can write 50 into 10 raised to minus 6 into this. From this equation we have to find out this VGS minus VTH value. VDS is given here as 0.1 minus 0.1 square by 2. So from this we can calculate VGS minus VTH value. So we got it here, VGS minus VTH is equal to 1.05 volt. We got it here, VGS minus VTH is equal to 1.05 volt. Now we are keeping this VGS constant as per the question. It means what will happen? This value will become here as a constant because VTH is not going to change. So this VGS, VTH is constant. It means this value VGS minus VTH 1.05 will become a constant. But VDS we are changing. So this new VDS now we will get it here as per the question, like their data is given as a 1.5 volt. So this VDS new is 1.5 volt. Now if we compare this VDS value with this VGS minus VTH, then we found that this VDS is greater than VGS minus VTH. So this is saying that if we are keeping VGS constant and VDS increased to 1.5 volt, previously it was 0.1 volt. So now this is satisfying this condition here. So due to this condition, it is saying that earlier this MOS was operating under the linear region. Now it is satisfying this condition. So this is saying that this NMOS transistor is operating into saturation region. So whenever it is operating into this region, now at this new operating point means VDS has become now 1.5 volt. So at this operating point, what will be their transconductance, we have to find out. So this condition is justifying that this NMOS is working into saturation region, and as we know that current expression in the saturation region, how it is, so that ID is equal to, or simply we can say it here as a ID sat or IDS sat is equal to 1 by 2 mu n COX W by L into VGS minus VTH whole square. So they had asked about the transconductance. So how the transconductance is defined? Transconductance is defined here. It is denoted by GM and it is defined here del ID sat with respect to del VGS. So let's say this as a equation number A. Then we need to differentiate this equation A with respect to VGS and then substitute that the values of the unknown parameters so that we can get it here this GM value. So if we'll differentiate this, then we will get it here this GM is equal to del ID sat divided by del VGS is equal to, so this will become here like differentiation of this square will become 2 into VGS minus VTH. So 2 and 2 for this one, it will be cancelling out, and then the differentiation of VGS will be 1 and VTH will be 0. So 1 minus 0, it will be 1. So ultimately this expression we will get it here mu n COX W by L into VGS minus VTH. So now we have to substitute the values. So here we will get that mu n COX W by L, as per the question it has given 50 into 10 raised to minus 6 into, from the previous one we had got VGS minus VTH is equal to 1.05. So after doing this, we will get it here 52.5 microampere per volt square. So we got this GM value here. This GM is equal to 52.5 microampere per volt square. This is the value we got it here. So this is the numerical answer type of the question, and the unit is already mentioned as a microampere per volt square. So it means the numerical values as an answer for this question, it will become 52.5. So here if you will see that their unit is already mentioned here. So this will become here 52.5. Their numerical values is 52.5, and by this way, this is the end of the explanation for this question. Thank you. So the question here is, the photocurrent of a PN junction diode solar cell is 1 milliampere full stop. The voltage corresponding to its maximum power point is 0.3 volt full stop. if the thermal voltage is 30 millivolt, their reverse saturation current of the diode in terms of nanoampere, round off to 2 decimal places is fill in the blanks full stop. This is the question they had asked in GATE AC 2024 from the subject of ADC, and topic is solar cell. So now if you see that here the given data what it has given, so this given data is this photo current, what we can denote this as a IL, is 1 milliampere, and here it has given the voltage corresponding to its maximum power point. So at maximum power point, whatever is the voltage we obtain, so that is called open circuited voltage. So that we can write it here as a VOC is equal to 0.3 volt, and their thermal equivalent voltage as a thermal voltage it has given as a 30 millivolt. So VT is equal to 30 millivolt. Now we have to find out the reverse saturation current for this photodiode. So here we know that this VOC for a solar cell, it is given as a VOC is equal to VT into ln 1 plus IL by IS. So this IL is called their solar cell photocurrent, and IS is called their reverse saturation current, what we need to find out in this question. So whatever the values given in the question itself, so we need to substitute here. This VOC is given as a 0.3 volt is equal to VT is given here 30 millivolt. So we can write 30 into 10 raised to minus 3 volt into ln 1 plus their IL value it has given as a 1 milliampere. So we can write 1 into 10 raised to minus 3 divided by IS. So we can solve this equation and we can get the value of IS here. So this IS is equal to 45.40 nanoampere. Their reverse saturation current, we got it here. This is called reverse saturation current, what we got it here, 45.40 nanoampere. So their unit is already mentioned here, so we need to substitute their numerical value. So we got it here as a final answer for this question is 45.40. So by this way, this is the end of the explanation for this question. Thank you.